Hello and welcome to our lesson on rational functions and asymptotes. So a rational function, just like a rational expression or a rational equation, is going to contain a fraction of polynomials. Now if it was just an expression, you would just have a fraction of polynomials. And you might be adding, subtracting, multiplying, or dividing those fractions of polynomials. If you have a rational equation, then you stick an equal sign in there. And if you have an equation, so an equal sign with a y in it and an x in it, then you're probably looking at a rational function. So the rational function is going to have, it's going to be an equation, it's going to have an equal sign, it's going to be the relationship between two variables, so we'll see x and y in there, and in the mix you should see the fraction of polynomials. So here are some examples of what rational functions could look like, just the equations of rational functions, okay? So just like the equations and expressions, these will contain a fraction of polynomials. Okay, and we need to be able to graph these things. Now I know we have technology that graphs for us, but simply putting the function into Desmos or whatever technology we're using is not going to be enough. We need to show our understanding of all of the aspects of the graph, and I'm going to show you what I mean in a second. So let's just refresh. In our function unit, we talked about the parent. It's important to know what the parent function looks like because it's the foundation for all of the other rational functions. Okay, so we're going to make a table to examine the graph of the parent rational function. And the parent rational function is just y equals 1 over x. So do you remember what happened when we tried to make a table of values here? Normally when you make your table, you can pick whatever you want for x, plug it in, get a y value back out, and you connect the dots, right? So we were like, okay, let's pick -2, -1, 0, 1, and 2. These are pretty standard numbers to pick. Some negatives, some positives, 0. If I plug -2 in, well, 1 over -2 is going to leave me a -half. If I plug -1 in, 1 over -1 is going to be -1. And what happens when I plug 0 in? Well, 0 in the denominator of the fraction, as we know, and we've gone over several times, it's not defined. I can't have one part of nothing. It's not defined, and therefore this function and graph is undefined at this point. So we won't be able to actually make a point on the graph that corresponds with an x value of 0. Okay? So what about 1? If I put 1 in, 1 over 1 is going to be 1. If I put 2 in, 1 over 2 in is going to be a half. So let's get this graph started here. We have a point at -2 and -1 half. At -1 and -1. 0, we can't do anything. 1, oops, this graph is going by 2's. Goodness. Did you notice that? Right, 1 is here, -1 and -1 are there, and there's graphs going by 2's. So I messed that up. Let me try that again. At -2 and -1/2, we're going to be here. -1, -1, we're going to be here. 0, again, we can't plot. 1, 1 is going to be here, and then 2.5 is going to be here. Now, if you remember what the graph looks like, you can, keep making the picture from here. But just so we can go along with the table here and have a full understanding of what's happening with this rational function, we probably need some more points on our graph. So what would happen if I continue to pick larger values this direction, bigger values of x? So I've put 3 on the bottom of the fraction. Okay, if I put a 3 in the denominator, then I get 1/3, or 4 in is 1/4, or 5 in is 1/5, and then 1/6 and 1/7, then what happens? Well, the fraction, if the bottom just continues to get bigger, the value of the fraction is going to get smaller and smaller and smaller, right? You'd have 100th eventually, and then 1,000th, and then a fraction that's really, really, really tiny. So the farther we go this way, the closer we get to the x-axis, because the smaller the fraction gets, but I can't ever get to the x-axis because that fraction will always have some value. Okay, so I'm going to get closer and closer to the x-axis as we go this way. And then the same thing, same thing is going to happen on the other side, but these are negatives, right? So I can put the negatives in, and we'll get closer and closer to the x-axis this way. So what's happening, if you recall, is we have this barrier in the graph that we call an asymptote. Right here, what's happening is we can't get to a y value of 0 because the fraction's always going to have some value in the numerator, right? No matter what number I put here, if I aside from 0, which can't go in, if I have 1 in the top, that means the function value, the y value, is always going to have some value. So I cannot get to a y value of 0, so we see this horizontal asymptote in the graph at y equals 0. Okay? Now what's happening in between here and here? Like, what's happening in this region of the graph, right? What happens if I pick some fractional values for x? So I got the 1. What if I put a half in? Okay, if I have 1 and I divide it by a half, well, that's 1 times 2 over 1, so that's going to be 2, right? So I put a half in, my graph goes up to 2. If I put a third in, now I'm multiplying by 3, so my graph goes up to 3. And then if I put a fourth in, then I'm multiplying by 4, my graph goes up to 4. And the smaller the fraction gets here, the bigger this number is going to get. So what's going to happen this way is we are going to continue to climb. But I can't ever plug in an x value of 0, so again, I can't ever get to that axis. And the same thing's happening this way. These are just going to be negatives. But we can't get here. Cannot get to an x value of 0. I can plug in infinitely small fractions, but I cannot plug in an x value of 0 because it makes a 0 in the bottom of that fraction. So here we see a vertical asymptote in the graph at x equals 0 because we cannot plug in an x value of 0. Okay, so the characteristics that we see here, meaning the asymptotes, and then the actual pieces of the graph we call branches. So we have a branch over here, we have a second branch over here. These are the same types of features and pieces that we're going to see when we generally graph a rational function. There will be some exceptions, and we'll go through those as we progress through this module, but for the most part, a rational function is going to have these asymptotes, and it's going to have branches on either side of the vertical asymptote. So in general, graphs of rational functions may contain asymptotes. That's what we call those barriers. Okay, may contain asymptotes. And again, those are those barriers. They're lines that the graph seems to be approaching, and they won't usually cross. Again, there's always these weird cases. Once in a while, you will have a graph cross an asymptote, but usually the graphs approach them without crossing. So these are lines the graphs get closer to, they approach without usually crossing. And for every vertical asymptote, you should have 2 branches. So if you have one vertical asymptote, you should have a branch on either side of it. If you had 2 vertical asymptotes, then you would have a branch, something going on in the middle, and you'd have another branch. So if you have, you should have 2 branches for every vertical asymptote. So you're going to have branches. These are the actual pieces of the graph. That's why they're the only ones that I drew in with solid lines on the graph up there. So it will contain branches to the left and right of each vertical asymptote. Okay. Now, why did we end up with a vertical asymptote? So which one was vertical? Vertical was the one going up and down. That's the green one there. Why did we end up with that vertical asymptote? Well, because there was a value of x that we couldn't get to, right? That we could not plug in. So vertical asymptotes in general will occur at restricted x values. If there are any values of x that are going to make our denominator equal 0, we know those are restricted, and those restrictions cause these vertical asymptotes in our graphs. So then why do we have, or why do we end up with horizontal asymptotes? So vertical asymptotes are going to be caused by restricted x values, and the horizontal one happened because our y's couldn't get to 0 in that parent function. So horizontal, again, that's going to be going left to right there, not up and down. Those are going to occur at restricted y values. And those aren't going to be as easy to see as the restricted x values, but we're going to talk about ways to find them. And then just like in our function unit, we talked about transformation rules. They still apply to our rational functions, and we saw them there. But I think this is a good place for us to review our transformation rules that still apply. Okay, so the standard form for a rational function, we've talked about the parent. The standard form is to take that parent function and possibly multiply it by some value of a, and possibly add something to or subtract something from the x value, and then possibly add or subtract something from the function. So our standard form includes this a, h, and k, where, just so you can see a concrete example, right? I could take my parent function 1 over x, and let's say I add 1 here, and let's say I subtract 1 after the function, and let's say I take this and I multiply it by negative. Well, we should know, based on the transformation rules that we talked about in that first module, what those things are going to do. So hopefully remember what the negative does, what adding 1 to the function does, and what subtracting or adding 1 to x does, and what subtracting 4 from the function does. So let's do a little tiny recap here. A, that's the number that we would multiply out in front here. That's going to affect the width of the graph, so it could, remember, vertically compress or stretch it. So it affects the width. And if it was negative, it could also be reflecting the graph. So it also affects whether or not the graph reflects. Okay? And then h, the number that we add or subtract from x, h, it affects whether the graph is going to shift to the left or to the right. So h is our horizontal movement, where that was the one that was a little bit counterintuitive. If we were adding an h there, that it would go to the left, and if we were subtracting, it would go to the right. And then if we, and that's add or subtract to x, if we add or subtract from the function, so like after the parentheses there, that k value is going to shift the graph up or down. And this one is intuitive, where positive adding makes it go up and subtracting or negative makes it go down. Okay, so just looking at number 1 here, I can see my parent function, right? There it is. So I know this graph is going to resemble that parent function, but because there's a plus 2 and a minus 3 here, this plus 2 and this minus 3 are going to move this entire graph. The plus 2 is going to shift this or translate this graph to the left 2 units, and then that minus 3 is going to translate this graph down 3 units. Okay? And how about the second one here? Again, I can see my parent function, so I know this graph would resemble the parent, but there's a negative in this one, and if you recall, that negative is going to reflect this graph over the x-axis. Reflects over the x-axis. And then there's a minus 3 here, and so when we subtract 3 from the x value, that's going to make the graph go to the right. It's going to translate right 3 units. Okay, and then lastly here, this negative, so multiplying the function by a negative reflects it over the x-axis. If I multiply x by a negative, then it technically reflects over the y-axis. And then the plus 5 here would translate this graph 5 units up. So this is going to go up 5 units. Okay, now why is it I guess I shouldn't say important. I was going to say or ask, why is it important to know these? It's important, but it's really more helpful than it is important, because there are other ways that we can go about figuring out where our asymptotes are going to be, or what these graphs are going to look like. And we know we have technology that graphs for us, but it's helpful to know these because we could sort of have a quick visual in our head of what this graph is supposed to look like. Or even if we had to sketch one of these graphs on paper and we can identify transformations, the sketching part should be pretty easy. So I want to show you, even though I realize you're not doing a lot of this work by hand and you're not submitting a lot of hand work, eventually, if you're going on to higher levels of math class, you'll have to be able to do this. So if we're going to use transformations to graph from standard form, so standard form, again, that's what we just looked at, those last 3. That's where we can see our parent function, and then we can identify that there are just a couple of transformations occurring in that parent function. To graph, or using those transformations, what I like to do is identify the point where the asymptotes are going to cross and whether or not we have any reflections. So what do I mean here? Okay, so I know that this is going to make my graph go to the left 1 unit, and I know that this is going to make my graph go down 2 units. So I can see by looking at this first function that I'm going left 1 and down 2. But what is it exactly that goes left 1 and down 2? Well, technically every single point from the parent function goes left 1 and down 2. So let me just sketch the parent in here. Don't do this on yours, okay? But the parent function had these asymptotes here, and there was a branch over here, and there was a branch over here. So if I have to take every single one of those points and shift left 1 down 2, that's kind of tough to do. So instead of shifting the entire graph, the easiest point to shift is this point in the middle where these asymptotes cross. Instead of shifting the whole graph, let's shift the asymptotes. Okay? Now I could actually shift the whole graph. Like if I took the whole graph, and moved it left 1 and down 2, what's going to happen is the point where the asymptotes cross, right? They land there. So what I like to do is, again, shift the point where the asymptotes cross. So on the parent function, the asymptotes cross at the origin. Okay? Well, now I know they're going to go, this point is going to go left 1, and it's going to go down 2. So now they're going to cross here, which means I'm going to have a vertical asymptote through that point at x equals -1, and I'm going to have a horizontal asymptote through that point at y equals -2. So left 1, down 2, or I just look at this because this is counterintuitive here. This is going to move the point where my asymptotes cross to -1, change that sign, and then keep that sign -2. So my asymptotes will cross at -1, -2, or left 1, down 2. Okay? And I'm going to come back and do this again, so don't forget. Alright, so we're going to also want to identify if we have any reflections, and there's no negatives multiplied here, so we don't have to worry about that. We're going to use a highlighter to draw in the vertical and horizontal asymptotes. And we want to make sure that we draw these in using dotted or dashed lines. And the reason we do that is because the dotted line or the dashed line says that those lines aren't actually parts of the graph. They're just visual barriers for us to show the graph can't go there, but they aren't actually the graph. The graph itself is just the branches, okay? But we want to show these. And then the branch part, if we were sketching this on paper, we would literally just sketch them. So we would just be sketching branches and just make sure that they're in the right quadrants. And again, there should be a branch to the left and right of each of the vertical asymptotes. And then luckily, again, we have technology to do this graphing for us and to verify our work. So we're going to use Desmos to verify everything we're doing. And because what you are going to submit is actually going to be from Desmos, I'm going to show you exactly what I want you to type into Desmos and submit in your practice assignment. Okay? So this graph is going to, again, this +1 makes my graph go left 1. And then this +1 makes the graph go left 1. This -2 makes the graph go down 2. So instead of my asymptotes crossing at the origin like they do with the parent function, then my asymptotes cross at left 1 would be -1, down 2 would be -2. So they're going to cross at -1, -2. So from the origin, left 1, down 2, that's where they cross. Okay, so now I'm going to use my highlighter to show that I will have a vertical asymptote there at x equals -1, vertical asymptote at x equals -1, and then I'm going to have a horizontal asymptote through that point, so a horizontal asymptote through that point at y equals -2. Okay, now since there weren't any reflections in this graph, those branches need to be in the same quadrants as the parent, and that would have been top right and bottom left. And it's just a sketch. I don't even really care when you're sketching here that, you know, where they cross the axis, whatever. I just want the branches to be in the right location. So really you should have a branch approaching the axes here, and then a branch approaching the axes here. And that's it. So now, I know we took a few minutes to put that all on paper, but that's really the visual that I want popping into your head when you're looking at this function. So I want you seeing the parent and being like, okay, if it goes left 1, down 2, I pretty much know what this graph looks like in my head. Okay, ideally, that's what's happening. Now, in Desmos, what do I want to see? So when you submit a Desmos picture to your practice assignment, obviously you're going to type your function in. So we have y equal to, let's make a fraction, 1 on the top, and then x plus 1 on the bottom, and then we have a minus 2. Now it's only going to show the branches, which, remember, those are the only actual parts of the graph. But that's not all I want to see when you submit this in your assignment. I want to know that you understand where the asymptotes are. So I also want you to show the asymptotes. So I want you to type in x equals -1 so that we can see that vertical asymptote. And I also want you to type in y equals -2 so that we can see that horizontal asymptote. And if you want to zoom, that'd be great. And anytime you zoom, if you've messed up your zooming, if you hit the little home button, it'll take you back to a normal window. Okay, so I'm just going to zoom a little more. Now remember, the asymptotes aren't really parts of the graph, so we want to show those with dotted lines. So I'm going to use the settings here, and I'm going to go into this green one, and I'm going to change that to either the dotted or the dash, doesn't matter. And then I'm going to make it, green's fine. And then this purple one, I'm going to change it to green also, just because I like green. And there it is. So that is the picture I want to see. I want to see your function, I want to see the equations for your asymptotes, and I want to see all three of those items in the picture. Okay, and make sure that you're zoomed in a way that I can see all of it. Alright, so that's exactly what you should be submitting. And I can see on my paper that's exactly what's happening there. Alright, so let's try another one. Okay, so this guy, this time has a negative here, so I know that this is going to be reflecting over the x. Reflects over the x. And then this -3 is going to make our graph go to the right 3. So my asymptotes are going to cross where? Well, I'm not shifting up or down, I'm just going to the right 3. So if I just went from the origin right 3, then I land here. So I go right 3, that's +3 this way, and I don't move up or down, so that's going to stay at a 0. Okay, so I'm going to have a vertical asymptote through that point, and that is at x equals 3. X equals 3, and we can see that here, right? X equals 3, that's my vertical asymptote. And then my horizontal asymptote is still going to be where it was with the parent function at y equals 0, because I didn't go up or down. So y equals 0, that's my horizontal asymptote. Now the reflection is going to affect the branches. Okay, in the parent function, my branches were here and here. If I take those pieces and reflect over the x-axis, if I make a mirror image over the x-axis, what happens is the branch here is going to land here. Okay, and the branch that was here is going to land here. It's going to make a mirror image over the x. So what I want is a branch to be here and here. So I want the branches in the bottom right and top left instead of the reverse of that. And that would be a perfect sketch of the graph. And let's just confirm. So I should have a negative, oops, let's put y equals a negative and then a fraction with 1 on the top and x -3 on the bottom. And let me hit my home button. There's those branches in the opposite corners than they were before. I'm going to type in my x equals 3. I'm going to type in my y equals 0. And then I'm going to change these to dotted lines. Come on. Dotted. And there it is. So that's exactly what I would like for you to submit. And you can see that that's just verification that what we did on the paper was exactly correct. Okay? Oops, hit that home button again. Alright, one more here if you want. I think this would be a good place for you to pause and check your work. So feel free to pause and see if you can figure out this one on your own. So here we have a negative again. This time it's multiplied by the x, so the reflection happens over the y-axis. Oops, I forgot the word axis up here. And then this +4 added to the function is going to make the graph go up 4 units. Okay, so where are my asymptotes going to cross? Asymptotes are going to cross at where? Well, if I'm just going to go up 4, then my x value is not going to move. If I'm going to go up 4, then I'm going to be at 0, 4, right? I'm not going left or right, I'm just going up 4. So 0, 4 is where they're going to cross. So I'm going to have a, vertical, I changed the wrong thing, vertical asymptote through that point. So my vertical asymptote is still at x equals 0, still at x equals 0, just like the parent. And then I'm going to have a horizontal asymptote through that point. So a horizontal asymptote at y equals 4, right? And again, I could see this here, y equals 4, because everything shifted up 4. And then my branches this time reflect over the y-axis. So think about this, right? Originally, the branches were in these corners. That's the parent were. If I reflect over the y-axis, then this guy is going to land here, okay? And then what's going to happen is this branch reflected over the y lands here. So a reflection over the x or y axis actually ends up with the same effect. We end up being in the opposite corners. So the x and y axis reflections cause the same effect on the graph. Reflecting over the x or the y makes the same picture. Okay? So there's that. And again, this is more for, it's not like you have to know this. It's not super, super important, but it is helpful for you to be able to look at that function and know pretty much what's happening with that picture. Now, it's only helpful if the function is given to us in standard form. That is, again, where we can see the parent function and then just some transformations that are going to apply. But not every rational function is going to be in standard form. It might not be the case that we can see the parent function and identify transformations. For instance, look at all these rational functions, still fractions of polynomials. Can you see the parent function in there? I don't necessarily know. Once we put x's in the numerator and denominator, we're no longer in that standard form. So we still have to be able to identify asymptotes, and we still have to be able to graph and show those asymptotes. So how do we go about finding those asymptotes when our function is not in standard form? Okay, let's look at the verticals first. Remember in the beginning we said vertical asymptotes happen because of restricted x values. And the restricted x values are the ones that were making our denominator, equal 0. That was no good. So those vertical asymptotes were caused by those x values that made the denominator equal 0. So all we need to do is figure out what x values make our denominator equal to 0. So we're going to set our denominator equal to 0, make a little equation out of that, and solve it. So set the denominator equal to 0 and solve to figure out where those restrictions are. Now, some of this solving we can do in our heads, I'm hoping. So x minus 6, if we find what makes that equal 0, all we'd have to do is add 6, right? So x equals 6 is our restricted value. That means we are going to have a vertical asymptote in this graph at x equals 6. So this is a restricted value, okay? That means we're going to have a vertical asymptote. I'm hoping we're okay with just abbreviating vertical asymptote VA. I did that already on the other side. But we're going to have a vertical asymptote at x equals 6, okay? And I guess just to avoid confusion, when I'm saying x minus 6 equals 0 here and x equals 6, what I'm really saying, because x is a restricted value, is that x cannot equal 6 because x minus 6 cannot equal 0. So because x cannot equal 6, there is a vertical asymptote at x equals 6, okay? So let's try that again here. This denominator, this 2x minus 3, any denominator, cannot equal 0. It can't. We don't want it to equal 0, and that's what's going to cause a vertical asymptote. So on this one, if I added 3 over, 2x can't equal 3. If I divide 2 over, that means x cannot equal 3 halves. So since x cannot equal 3 halves, since there is a restricted x value of 3 halves here, this means we will have a vertical asymptote at x equals 3 halves, or 1.5. Okay? How about this guy? Again, this denominator, in this case x squared minus 4, it cannot equal 0 because that is not defined. Now x squared minus 4 is going to give us two restrictions. Hopefully you're recognizing this difference of squares factors into an x plus 2 and an x minus 2. So if neither of those can equal 0, that means x cannot equal -2 or +2. So what does that mean about this graph? It means this graph is going to have two vertical asymptotes. This means it's going to have a vertical asymptote at x equals -2 and at x equals +2. Two vertical asymptotes. And just so you can see, let me delete all this out. You can confirm what you're doing here, and just so you can see what it looks like when you have two vertical asymptotes. Let's see, y equals, let's put a 3x minus 1 on the top, and let's put this x squared minus 4 on the bottom. Look at that. So I have a vertical asymptote at x equals -2, and I had another one at x equals +2. And you can see there's a branch to the left of the whole thing, to the right of the whole thing, and there's that branch that actually crosses the horizontal in the middle. So just confirming, and just you can kind of get an idea of some of the fun we have headed our way. Okay. Again, here's an opportunity for you to try one. Feel free to pause the video. If we know this denominator, 4x plus 1, if we know it can't be 0 because it's undefined, then we would subtract 1 from both sides and divide both sides by 4 to see that x cannot equal -1/4, which means this graph is going to have a vertical asymptote at x equals a -1/4. Okay? So, vertical asymptotes, I think, pretty straightforward. They're just the same thing as finding restricted values, which we were doing when we were solving. And the solving there is not so bad, okay? And again, everything could be confirmed with Desmos. So, we can find the vertical asymptotes. It's the horizontal asymptotes that are a little bit strange. I'm going to show you a way to find them. I wish I could explain a little bit better why what I'm going to show you works, but it connects to some calculus and some levels of math that we just aren't ready for yet. So you're just going to have to trust me on some of this. But we're going to look next at finding the horizontal asymptotes. And again, this is when it's not in standard form. Because when it's in standard form, I can see my graph shifting up 1, then I know my horizontal asymptote goes to +1. Or if I can see it shifting down 4, I know the horizontal asymptote goes to -4. But if it's not in one of those forms, what do we do? Well, the horizontal asymptotes, as we said in the beginning, they happen because of restrictions for y, restricted y values. They just aren't as visible, as I mentioned, as the restricted x values. What they're based on is the degree of our numerator versus the degree of our denominator. So we have to find the degree of the top and bottom of the fraction and make a comparison. Now what's going to happen when we compare two numbers? Because the degree from the top is going to be a number and the degree from the bottom is going to be a number. Well, either the two numbers are the same, or the first number is bigger, or the second number is bigger, right? Those are the three options. So if the degree of the numerator is, let's start with less. If it's less than the degree of the denominator, so the degree of the numerator is less than the degree of the denominator, then what happens is the horizontal asymptote is going to be at y equals 0, just like the parent function. Okay, remember the parent is 1 over x. Here the degree is 0 because there's no exponents on variables. On the bottom the degree is 1, and that 0 is less than 1. And so anytime that happens, anytime the degree of the top is less than the bottom, just like the parent function has a horizontal asymptote at y equals 0, so will any rational function with those properties. Okay? Now if the degrees are equal, if the degree of the numerator is equal to the degree of the denominator, so the numerator and denominator have equal degrees, then we're going to divide our leading coefficients to see where our horizontal asymptote will occur. And then the last case would be the degree of the numerator is greater than the degree of the denominator. When this happens, then there is no horizontal asymptote. So when the numerator degree is bigger than the denominator, then no horizontal asymptote is going to occur. And again, this could all be confirmed by putting it into the calculator. You're going to put it in there and you're going to see, oh yeah, I did this right. Okay? So let's look at number 10. The degree is the highest exponent that we see on a variable. So in this case, the degree of the numerator is 1. So this has a degree of 1. and the degree of the denominator is also 1. When the degrees are equal, it says here to divide the leading coefficients. The leading coefficients are the first coefficients. So the coefficients I'm dividing here would be the 3 and the 1. So I'm going to have a horizontal asymptote at y equals, so the horizontal lines are y equals 3 divided by 1, which is just 3. Okay? It's a little crazy, I know, but there it is. And if you weren't sure, again, you could confirm this, okay? Let me just show you. Y equals, put a fraction in here, 3x plus 1 on the top, x minus 6 on the bottom. So I'm going to zoom so I can see it. I'm saying, based on the math I just did, that this is going to have a horizontal asymptote at y equals 3. Let me put it in here and make sure that it looks right. And yeah, I can see those branches approaching that horizontal line at y equals 3. Okay? Alright, let's try this one. On the next guy, the degree of the top right there is 2. And the degree of the bottom right there is 1. So this time, the degree of the top 2 is bigger than the degree of the bottom. And anytime the numerator is bigger than the denominator in terms of degree, then there is no horizontal asymptote. Okay, over here, these are equal. It's fine. And again, we can confirm this. And I don't want to kill your time here, but just so you can see what a graph looks like when it doesn't have a horizontal asymptote. Y equals, on the top we have x squared minus 4 on the bottom, 2x minus 3, and no horizontal asymptote. There appears to be some kind of a slanted asymptote happening in there, and we will get to that, okay? But no horizontal asymptote. Alright, the next one. Degree of the top is 1, degree of the bottom is 2. So the degree here is 1, and the degree here is 2. This time 1 is less than 2. The top is less than the bottom. So just like the parent function, there's going to be a horizontal asymptote at y equals 0. Okay, and again, you could confirm it with your calculator. And if you want to try this last one, the degree of the top is 1, degree of the bottom is 1. So when the degrees are equal, as they are in this case, we're going to divide our leading coefficients. So the 1 here divided by the 4 here. So this is going to have a horizontal asymptote at y equals 1 divided by 4, which is going to stay 1/4. Okay? And I guess I shouldn't have erased what we were dividing here, those leading coefficients. Alright, so I got one last one here. We're going to try to produce this graph, and then we'll confirm our work in Desmos. This graph, I can't just look for transformations and plot a point and say my vertical asymptote and horizontal asymptote has to be to that point, because this is not standard form. So when it's not in standard form, let's find our vertical asymptote using our denominator. Vertical asymptote, we know that our denominator x plus 1 cannot equal 0. So x cannot equal 1. So there's going to be a vertical asymptote at x equals 1. So I'm going to go to x equals 1, it's right here, and I'm going to make a vertical asymptote through that point. Okay? Now the horizontal asymptote, I want to look at my degrees. So my horizontal asymptote, I look at the degrees. The degree of the top is 1, that's the highest exponent there. The degree of the bottom is also 1, and so I'm going to divide my leading coefficients. So 4 divided by 1, which is just going to be 4. So a horizontal asymptote at y equals 4. So I'm going to go to y equals 4, make a point, and I'm going to draw my horizontal asymptote through that point. Now, it's not a transformation of the parent, so I don't know where the branches are going to be. So I'm going to go to Desmos to find out where I'm going to put these branches, and then to confirm all of my work. So y equals, fraction button, 4x minus 5 on the top, x plus 1 on the bottom. And so now I can see, oops, home button, where my branches belong. So branches need to be in this corner, that is top left, and this corner bottom right. Okay, so there's your sketch. Now in Desmos, what are you going to submit? You're going to submit that graph, and you're also going to confirm that the vertical asymptote's happening at x equals 1. Oh, look at what I did, guys. It's not 1. X plus 1 has to equal 0, means x has to be, or can't be, -1. Son of a gun. Okay, that should be a negative there. Some of you are probably watching me going, what is she doing? That should be a -1 there, which means I gotta fix this. Ugh. My bad. Almost made it to the whole thing without goofing. Okay, -1. Let's try that. And +4. That one's still fine. Nobody said anything to me. I'm goofy. I'm sorry. Branch. This is why it's good to confirm your work. See? Found a mistake. Okay. So x equals -1. Hey, that looks better. I see the branches approaching there. That asymptote shouldn't have gone through the branch as it did before. And then a y equals 4. Does this look right? Yeah. And let's just make those dotted lines. So let's go dotted, and then dotted, and let's make that the same color. And there it is. So I want to see all of that in the picture that you upload to your practice assignment. Okay? It's a lot of information. Take some time to digest it, work through some of those practice problems, and as always, reach out if you need.